All right, today we're diving into a revolution that's happening deep inside our computers. Seriously, it's a huge shift in how they handle multitasking, and it's taking us from systems that could grind to a halt to ones that are just incredibly fluent. I mean, really think about it for a second. You've got a file downloading, you're typing away in a document, maybe you've got music streaming, all at the same time. How on earth does your machine juggle all of that without just locking up? It's a fantastic question, and the answer is right at the heart of how modern computers work. Okay, so here's the fundamental problem. Your computer's brain, the processor, is ridiculously fast. We're talking billions of operations a second. But things like reading a file from your hard drive, or even worse, fetching something from a website, that's just painfully slow in comparison. If your super fast processor had to just sit and wait for every single one of those slow jobs to finish, your computer would feel like it was stuck in molasses, constantly. So to get around this, we came up with a really clever trick called multi-threaded processing. The idea is brilliant in its simplicity. If one task is stuck waiting for, say, the network, the system doesn't just twiddle its thumbs. Nope. It instantly switches over to another task that's ready to go. This happens so fast, back and forth, that it creates this perfect illusion that everything is happening at once, and it's what keeps our apps feeling snappy and responsive. For decades, the one and only way to do this was with something called a platform thread. You can think of this as the original hero of our concurrency story. So what even is a thread? The simplest way to think about it is that it's the smallest possible chunk of work that the computer's operating system can manage. It's like a single lane of traffic for instructions. A single app can have tons of these threads running side by side. Now, this is the crucial part to understand about the classic approach. A platform thread, the kind we've used forever, has a direct, one-to-one mapping with a thread managed by the operating system itself. That one-to-one link makes them powerful, sure, but it also makes them heavy. Each one takes up a real chunk of memory and system resources because the OS has to keep a close eye on it. And that direct link to the OS, well, that's where we find the hidden flaw. It turns out our classic hero, the platform thread, has a pretty serious Achilles heel, especially when we start building the kind of massive applications we need today. This is just a fantastic analogy. A platform thread is like hiring a dedicated, full-time butler for every single tiny task you need done. If that task is just wait for a package to arrive, your expensive butler, this very real, resource-intensive thing, just stands by the door doing absolutely nothing useful. It's not exactly an efficient way to run your household, right? And this slide just lays it out perfectly. On the left, you've got the dedicated butler model. That's our old platform thread. Heavy, expensive, and often just waiting around. On the right, you have the efficient server model. That's the new idea, the virtual thread. One server who can handle many, many tables. So let's put this old model to the test. Let's do something a little nuts. Here's some code that tries to create and run 1 million of these platform threads all at once. Each one doesn't do much, just waits for a second. It's a pure stress test of the butler model. Any guesses what happens? Yeah, it fails. And not just a little bit. It fails catastrophically. The program doesn't even get off the ground. It just crashes with a big, fat, out-of-memory error. The system simply cannot handle hiring 1 million of these heavyweight butlers. The classic approach hits a hard wall when you try to scale it. This spectacular failure really sets the stage for our new hero. To solve this million-thread problem, we need something completely different. We need a revolution, and that revolution is called virtual threads. So how do we fix our code that crashed and burned? Well, take a look at this. The change is so small it's almost funny. We just swap out one word. Instead of thread.of-platform handling, we say thread.of-virtual handling. That's it. We're just telling Java, hey, use that new lightweight model, not the old clunky one. And what happens? It works. It works perfectly. 1 million threads pop into existence, they all run, and the program finishes up in about a second. No sweat. This is just such a powerful aha moment. The exact same task that was literally impossible before is now completely trivial. So what's the magic trick? This slide explains it all. On the left is the old way. One platform thread, one OS thread. Heavy. On the right is the new way. See how all those little virtual threads aren't directly tied to an OS thread? Instead, they're running on top of a small handful of real threads, which we call carrier threads. So here's why this is a total game changer. Virtual threads are managed by Java, not the OS, which makes them super cheap and fast to create. And here's the killer feature. When a virtual thread has to wait for the network, it just steps aside. It gets unmounted from its carrier thread, freeing up that precious OS resource to go run another virtual thread that's actually ready to do work. It's like an incredibly efficient game of musical chairs, and it's what lets us achieve this massive, massive scale. Now, with this incredible new power, it turns out we also have much better, more modern ways to manage it. The old way of manually creating and starting every single thread is, frankly, a bit outdated. Trying to manage the lifecycle of every single thread yourself, it gets complicated fast, and it's really easy to make mistakes. The modern way to do it is to use something called an executor service. You basically just package up your tasks and hand them over to the service, and it takes care of all the messy details of running them on threads for you. And this executor service gives you two main ways to give it work. The first is called execute. This is your fire and forget option. You just tell it, go run this, and you don't care about getting anything back. The second is submit. You use this when your task is going to produce some kind of result, and it hands you back a special object to deal with that. And that special object is called a future. Think of it like a receipt or a promise for a result that isn't ready yet. Your main program can submit a long-running task, get this future object back immediately, and then go off and do other stuff. It doesn't have to wait. Then whenever it's ready, it can check the future and say, hey, is my result here yet? It's a really powerful way to write code that doesn't get blocked. And really, this quote just nails the whole philosophy here. The goal of all these modern tools, from virtual threads to the executor service, isn't just about raw speed. It's about giving all of us the tools to write these complex, multitasking programs in a way that's safer, more efficient, and just as importantly, much easier to read and understand. Which brings us to a final, really exciting thought. For years, software has been designed around the fact that threads are expensive. We've built entire architectures to work around that limitation. But now, that limitation is just gone. Now that we can effortlessly handle millions of concurrent tasks, what does that unlock? What new kinds of applications can we build when that fundamental constraint is lifted? That's the really fun question we get to figure out next.